long time. Does everyone remember what we're doing? So we're looking at the cumulant expansion of this Landau-Ginzburg-Wilson functional. And we've imposed this condition essentially of self-similarity in the functional integral to give us the functional or the action, after one step of the RG, right? And we've calculated already sort of the non-interacting piece and the interacting piece coming from the first cumulant in the cumulant expansion. And we're like halfway through figuring out what's going on with this second piece. So the first piece, if you dig back somewhere in your notes, right, just the usual phi squared term, k squared plus r, okay. And you have an integral over the slow modes. The first cumulant, the first order cumulant interacting piece, we've already studied the combination of these two pieces. Gave you something like this. Slow fields. I remember that came from, we called it the D term. In those 5 different terms that we had to look at the integrals for. The combination of this piece and this piece, so the first order contribution from the interacting piece, gave us the same fixed point as we've seen like 4 times now, which is that Gaussian fixed point. It was at U star and R star equals 0, right? So we've analyzed these two pieces by themselves already. And so what Wilson and Fisher did was just, say we have to keep pushing to higher and higher order in the cumulant expansion to try to see if we can get some non-interacting, some non-trivial fixed point from the interacting terms. Because we're still searching for that. It's like, in the Ising model, we've argued in the Ising model at the beginning of class especially that you have a phase transition, right? And that phase transition is what we haven't found yet. We've only found the fixed point associated with maybe the trivial 0 temperature or infinite temperature cases. We haven't found anything to do with that phase transition. So we know physically it exists, and we're still searching for it in the RG here, right? So that last term, I had written somehow, see if I can do this right. Kept that minus sign. So I have this interacting piece squared. So last time we looked at this graphically, and I said there was, I'm not going to use colors. I'm not sure they turned out very well. So I'm just going to use dash for fast and straight for slow. I don't know. Anyway, there's a whole bunch of these. That's all the squared terms. There's 25 of them. Right? There's like 5 terms, A, B, C, D, and E. And this is all the possible pairings of those terms. And then we have the other part of the second cumulant, which is 2 of these things. And there's 5 terms, A, B, C, D, and E, inside each one of these. And remember, each one of those vertices, it's just a graphical representation of the delta function that occurs inside the integral. And then the lines are the fields. Okay, so and what did I say? Straight lines are slow fields. One of those was yellow or something last time. And I spent half the class looking at all the terms in these expansions and sort of vaguely arguing for which ones are important. And I convinced you that the only diagram we have to consider in the second cumulant is basically this one here. Slow fields, so 4 slow fields. That's like the product, it's like combining the fast fields in the first element of that first S in squared expectation value. And remember, there's a combinatorial factor of 25 or 36? 36 in front of this one. Which you have to get right if you want to get the fixed point right. Okay, so that's where we are. We now have to just evaluate this basically diagram, what this means. This integral, its expectation value over fast modes. Right, I have 2 of these delta functions, and I have these 6 fields. And so that's all there is to it. I just have to do that integral now. And that'll be my second order piece, okay? So let's look at this. So I'm going to label momenta on here now. I'm going to give them labels K for the slow fields. And Q's for the fast. Okay, so I've just made up those labels, but they're constrained by the delta functions, right? So the delta functions say so everything going into this vertex, so I'll assign signs to them. Okay, so that assigns basically a direction for each one of these momenta. And also from this vertex, right, so having the 2 delta functions together, right? There's 2 fields shared between the 2 delta functions. These Q terms here. So that gives some constraints, and you could see right away that K1 plus K2 plus K3 plus K4 equals 0. And if I let, let's say Q1, we'll just call that one Q. Then Q2 is constrained to be minus Q minus K1 minus K2. Right. So that diagram let me write the integral. Did I define this as a factorial before, or is this a slip of my... I don't have my previous notes. I got a feeling no. Well, whatever it is, there's two of them here. No factorial? Okay, good. Okay, so I have these four fields. I guess I'll write them here. K1, K2, K3. K4. I thought I had more room. And I have to integrate over the fast fields, right? That's the point with these two lines here. And just like before, those integrals, I can write them in terms of the propagator. Okay, so again, it's an expectation value over the fast modes. That's this integral. And minus Q here. Good. Maybe I should call that the expectation value of that diagram. I don't know. So that's the one that matters. So that's the only thing we have to do. We basically know what these are, you know, and then we're going to have the four slow fields that we need. Because what we're doing is we're renormalizing the U piece, right? We're trying to find it's like we're trying to find the higher order, or this, you know, the U squared piece, so that we get a non-trivial fixed point in the RG recursion relations. That was the whole point of this. So yes, we have the U squared, which has to come out of the second cumulant. And we have the fields and everything that's going to make this self-similar, because this term has to be self-similar, except we have to worry a little bit about this. Okay, so let's just look at that piece. We have to do that integral. So let's call it something. I2. Uh-oh. And we know the form of those G naughts. Well, let me just write them out. So we've done one of these types of integrals before. I think it just had a single G naught in it. So let's see, it was like this, right? But we have another one here, which is 1 over, let's say R, and then that thing is my okay, if you're not sure about this, it's your first question on assignment 4. Okay, so like again, we knew how to do this integral previously, but now we have this extra piece, and it has these two K fields we have to worry about. So we can just look at the form of this thing. Oh, let me write below it here. And imagine pulling out an R, so that's like a 1 plus all that nonsense over, well, okay, we can expand this piece out. Okay, so take that square and then expand that as a series, that 1 over whatever that remaining thing is. So that expansion will give you something like what do I want to pull out? I'm going to pull out an r plus q squared also from this piece, okay? And then I'm going to expand what remains. So it's going to be 1 minus something. I got to make sure I get this right. So it's 2q all over. Plus higher order terms. So that's how that will look. So what I'm imagining doing is taking, handling this integral, one term at a time. And the first term is going to be fine. It's going to give us, basically the 5/4 back again. But what happens with all these higher order terms? And so these higher order terms turn out, you could work it all out, but it turns out that it gives you, higher order phi terms in your Landau theory, like phi squared, grad phi squared, and stuff like that. And so this integral is another indication that the form of the functional isn't fully closed under this RG step. We already saw one of these. I think it was one of the diagrams gave us a phi 6 term. These are going to give us terms that are higher than phi 4. Okay, so some of the same thing that I said happens in the real space RG is like happening to us here. But we're just going to ignore this. And I'm going to justify all of that someday, if I remember. So these terms, if you completed the Fourier transform back, whatever. I don't know what they all are. Okay, so we're just going to drop those and worry about them. And not to keep you in suspense, the point is that all of these other terms result in irrelevant couplings. Okay, so we haven't shown that yet. So what we're dealing with is only couplings that I'm kind of a priori selecting because we know are relevant under some RG flows. So all these additional pieces won't matter. But if you're the first person to do this, you can see why you'd want to quit. But Wilson and Fisher never quit.
Hold it down about 6 to 8 inches because I'm talking about I just want to be able to see that diagram. So you get that too far because it's walking together from here. So
It moves this one, so I can't control it.
You've got extra board rubbers, you can sometimes waste it.
Just write it quick. Okay, so what am I doing? Okay, so that's my I2. Okay, so let's solve that. Oops, I just wrote it again by accident. Damn. Okay. So let's see, we want do it in spherical polar. So I'm going to pull out that surface area. We've done this before, remember? So the only difference is we have a square here. Very similar to what we did before. And just like I did there, I'm going to expand out the denominator. So it'll look like this. So I'm going to pull out a Q4. Oops, 2. Okay, that's all we need, I think. Yeah. Yeah, that should be good. Okay, so we can do these integrals. Okay, just got 2 limits of integration. We'll do the 2 terms. Like this to give us okay, that's the first piece. Okay, I'm just going to factor out the lambda, the big cutoff, the momentum cutoff. So this one will be 2r. Forgot my 7 here. Oh, that's what that's supposed to be. That's weird. So it's 6. Oh, God. Okay. Yeah, okay, I think that's right. You know, so there's not really a lot of algebra in the end, right? Once you kind of know what to throw away. So you solve this integral now, you have these 2 pieces, and now really all you're doing is plugging that integral in and doing the RGE step, if you will, and analyzing what this is giving you. And again, you got to worry about all these additional terms and stuff. But so to do this, let's write the differential RG step in terms of that thing L. So all these terms that are like, this is how we did the analysis for the Gaussian case when we just had the first cumulant. So we'll use the same. So I'm doing, so it's up to power n. So it's n, I'll call it delta L. And the point is L, delta L, whatever is infinitesimal. So you expand that exponential. So it's 1 minus 1 plus to n delta L, right? So then I can write I2 There's all the cutoff dependence. And let me just keep those two terms. So this is what we'll use when we're talking about I2. Delta L R plus. I've actually just collected all the terms in this series. That works. That's nice. It looks very similar to I1. Actually, I'm not even sure what the difference is. I think it's just maybe this square here. Makes sense, sort of. Okay, so again, this expectation value of this single diagram. I2, there it is right there, and then all the slow fields. So that's it. So that now you have, the contribution from the second cumulant plus those additional two contributions, the one from the Gaussian plus the first order contribution from the cumulant. So you got to put all these together to give you your RG flow equations. And that'll give you S prime, right? So that's U to get S prime. Simple. Did that work? No way. Okay, so I just erased everything we need. Plus R plus 3UI1. That's from the first cumulant, remember? So those are the first two terms that I just erased. And let's see. Then I have my phi4 term. Plus, so that's the one with all the slow modes, right? Plus the diagram that I just calculated. So this is the new term. We had this term before, like I say, just from all the slow modes. And this is 4Ks. What? 4 slow fields. Is that everything? I believe so. Now, rescaling, K goes to B times K. And we know the fields. We know how to rescale the fields. So I won't do all that. You can do it for fun. We already know what these are, so. Remember the scaling dimension of the field was something weird. And that's what your slow fields turn into. Remember again, the philosophy is, if you have fields within that inner sphere, then you have that outer shell. So we've just integrated over that outer shell. And we're left with integrals that go from 0 to big lambda over b. And that's what defines the slow fields, right? So now those turn into our new fields over the whole Brouillon zone for the next step of the RG. Okay, so from this, you get this equation and this. 36 over, yeah, I got to pull U, okay, yeah, U squared I2. And this will be 4 minus D, like it was before. So that's your two RG equation, recursion relations. So remember, like I said before, you needed a U squared term here in order to get some non-zero solution to the fixed point. So there it is. So that's it. Now the rest is just analysis of this equation. Any questions about how I got that? You'll never do that much work again in this class. However many lectures that took. And I gotta say, I glossed over all the diagrams. So, Ken Wilson was working on this in the 70s. I think this basically, he broke this all open. I'm not sure exactly, but in the early 70s, like 71 or 72, everyone started picking up this. Everyone started to understand that, you get these non-trivial fixed points in this manner. So that's really what made the RG, I think, widely applicable to all these interacting systems that we study in condensed matter. Otherwise, if you're just dealing with Gaussian theories, in some sense everything's trivial. All the integrals are Gaussian, but there's no kind of non-trivial phase transition behavior. So how do we see, let's calculate, well, let's write these in differential form, then I'll solve those to calculate R star and U star. So you know they're going to be non-zero, but let's find out exactly what they are. Let me write I1 and I2. Because we're going to start looking at the dimension of this stuff. Right? Yeah, so this is the I2 contribution. So it's not so different. Okay, so the fixed point is when, remember this is like the change in the parameters, as a function of L, which is parameterizing the RG flows. So when that derivative goes to 0, it's like those aren't changing anymore, right? And so that's the solution for the non-trivial fixed point. For any fixed point. Okay, so the second equation is the only important one, or the most important one. So now that thing's going to give us U star. Yep, so it's going to be 4 minus. Let me just do this approximately. Yeah, near d equals 4. So I can write this as in terms of epsilon, which is going to be our expansion parameter. So then I can write this as epsilon over 9. Okay, so the idea is we're assuming that the distance from 4 dimensions is small. And then that's the expressions we'll use. Epsilon over 9, 2 pi over 4. Yeah, that's right. Okay? So that seems crazy. And it is. Okay, from that, let's see. Actually, I know what S4 is too, right? So I can write in terms of that. 2 pi d over 2 gamma 1, oh gamma 2, right? 4 over 2. Yeah, I like that better, so. Oh, 2 pi squared. Yeah, okay, I've seen that before. 8 over 9, epsilon pi squared. That's cool. So it's non-zero. But if epsilon was 0, then it's 0. And why? It's because we expect that 4 dimensions, right, the mean field exponents are the correct exponents, right? And the mean field exponents come from the Gaussian fixed point. So that's all self-consistent. So let's plug this into the first equation and solve for R star. And let me try to write this in terms of epsilon too. It's going to be squared here. Yeah, okay, so then this one's minus. Yeah, and that's right. So it's also linear in epsilon. So that's the ones we'll use. Okay, so that's the Wilson-Fisher fixed point.
So how can a dimension be like epsilon close to 4? Would it not be just a whole number?
Yep. That's why it's crazy. That's what I said. So it's, basically you're looking for a theory in 2 and 3 dimensions. So epsilon's either 1 or 2. But like I said, just like, I don't know, crazy things work. Like, spin wave expansions, 1 over s when s is a half. Those work too. There's just another thing that works. I mean, I'm sure there's a deep reason that you have to ask Sungsik what it is, but. So, you expect that 3 dimensions is to be hopefully fairly accurate, and 2 dimensions, you're getting farther away from epsilon, so you expect the accuracy to. So if you do epsilon expansions for the critical exponents, say, you would expect them to be most accurate in 3D and less accurate in 2D. And as we know in 1D, this fixed point doesn't exist because we already looked at the RG flows in 1D essentially. So it's only those 2 cases where you want to do the epsilon expansion.
When you substitute the U star into the first equation of differential form,
Yep.
so how is the lambda squared came from lambda to the d over r with lambda squared?
Oh, this one here? Let's see, so it's lambda to the 4. Let's see how many steps did I skip here. So this is the piece from, okay, so it's the same. Oh, so that's S4 here. Right, so I'm just taking, when I have lambda to the 4 minus d, so if I expand that out, then I'm taking that to be 0. I'm taking 4 minus d to be 0. So I'm just taking this limit to simplify that term as much as possible. I don't know if I'm answering the question. I'm just guessing what I did without going through it all. Oh, this square? Is this wrong? Is this supposed to be 4? Is that what you're saying? No, I don't think so. Because I have lambda d. So I have lambda d's that cancel at some stage of my U star here. I don't know. I don't want to work it all out. I'm too lazy. I skipped right to the end, which I assume is right because it gives me the RG fixed points correctly. So check that. Make sure it's right. But let's move on and analyze the flow. So I have a non-trivial fixed point, and what I want to know is where its relationship is with respect to the Gaussian fixed point. And I also want to know in dimensions less than 4, what's relevant and what's irrelevant. Okay? So I have this differential equation. I have the position of the fixed point. Let me go back to, let's see, I can write out, since I skipped too many steps that time, let's just remember what everything is. So let me define SD let me define something called K. So let me go back and look at these here. So then I can write at 4 dimensions that, okay? So I'm going to use that. So then my differentials become this r plus squared, okay. Oh, I want 4, right? Actually, it's general if I leave it as b, but I'm going to use 4. Okay, I think that's all I wanted to do. Okay, so now what I want to do is, so remember we had that T matrix? Remember all that? You have that T matrix, you find the eigenvalues and the eigenvectors. I want to do it with these equations. But that T matrix worked with the RG equations written like that. Remember? So I had something that was like delta R prime, delta U prime. Is this right? Then it was T, delta R, delta U. And I found the eigenvalues of that matrix at the fixed point. So all I got to do is take that analysis, but in this case it's easier to work with something like this. So it's not the T matrix anymore that I have to diagonalize. So what is it? And I think this is more standard what I'm doing now when you have these differential RG equations. So when you have non-trivial fixed points, it's easier just to work in what's called, I guess, an M matrix instead of a T matrix. Or a beta equation, it's called sometimes. Okay, so let's just remember what we're doing. I had some parameters, so let me keep it general. Remember, call them K. I have an equation that's like K minus K star. That's like my delta, K. And then I have a scaling dimension defined like this. And this is just K minus K star. Okay, so K can be U or R. So that equation I wrote over there, comes from analyzing this equation and using, but now I don't want to use those equations, I want to use the differential equations. So b to the y, right, so it's E y delta L then. Right, okay. If I expand that exponential again, which is why you do this, then you have y delta L delta K. Okay, so let me write it like, right, so I can bring that 1 over. So I want to write that differential. Y what? Delta K. It's the only thing that's left, right? Okay, I think that's... So this is like the derivative in delta K. Okay, and that equals the scaling dimension, delta K, so it seems crazy, but so I would call it this part. I would call this equation this. So before, like that T matrix gave us, say, lambda to the lambda i's. That was the eigenvalues of that T matrix. Okay. Now I need eigenvalues that are directly equal to y. Okay, so this is sort of simple, but I'm just transforming the language from that into this differential. So I call these things u. These are eigenvectors and lambda I, where lambda I was like b to the yi. Right, so there's one equation for every, well, two equations in that case, one for every eigenvector. Now I have something that's like the derivative with respect to L of u. And this, again, this is unfortunate notation. This is the eigen, or this is the scaling variable, not that u. So I'm using u tilde. So here I directly want, like from this equation, yi. Okay, so yi is the eigenvalue of the matrix. That's not T, but it's the equivalent of T. Or it's the equivalent of T for the differential RG equations. So for us, I'll just write it for R and U. Oops, not a fraction. Okay, so same philosophy, just slightly different analysis here. And so what M is, then, T was the derivatives. It was like R prime over R, right? So, actually, let me define the betas first. Let me define, so it's delta. Okay, so it's the derivatives right there. Okay, and then this M is the derivatives of those betas. So it's R, U, U, R. Evaluated at the fixed point. Okay, that's slightly annoying, but in the future, when you see a differential RG equation, which is the standard, this is the analysis you do here. You calculate the M matrix instead of that T thing that we've, in the easier cases, T was easier. And then the eigenvalues and eigenvectors, so the eigenvalues give you, in that case, the y's. They directly give you the scaling dimensions. Okay, so now let's analyze this. I think this is the way I want it. So I take the derivatives, all those four derivatives, and I evaluate them at the fixed point. I form that matrix, and then I just calculate the eigenvalues. That'll tell me the scaling dimensions, and that'll tell me whether or not the associated directions, not necessarily U and R, but the linear transformed u tilde u and u tilde r are relevant or irrelevant. So that's where this goes. I'll bring your assignment 4 on Friday, and I'll have a couple of questions where I just give you differential RG equations like this, and you can do some of this fun analysis. Oh my God, do I have to do all these derivatives? I guess so. I'll just do them quick and then check. So I need these, and I might as well just evaluate them at the fixed points. I wrote them down. Okay, let's use D here. All right, so convince yourself that this is something like 2. Oh yeah, so let's cancel. So this is actually just 2 minus, I think it's a third epsilon. Sure. So what I did here is I plugged in that fixed point, right? Could be, and I do the derivative with respect to u at the fixed points. Whatever, plug that all in. I get minus epsilon for this one. U, yeah, so the last one's R at the fixed point. What's this one look like? Okay, so I have a 1 over R plus lambda squared all squared. So somehow this one's just going to be proportional to U star squared. Right, because the first term doesn't have an R in it, so we're just gonna neglect that one. We don't need this. We need this piece. So that'll make our matrix easier to solve. It's order epsilon squared. That's another way of thinking about it.
Is that a partial derivative there?
Yep.
Right, so it's
It's just standing at attention. Yeah, those are all the elements of that matrix. They're all partials. Good, so the M has an easy eigenvalue equation. So this is the eigenvalue associated with, I guess, the R direction, or the reduced temperature, and minus epsilon for the U. Sometimes it's called R. So you got to check the directions again, right? You're in RG flow space. That tells you relevance and irrelevance, right? Assuming epsilon's positive, this one's negative, and so on. But it's not clear. You need the eigenvectors to know which direction these RG flows, or these relevance and irrelevant, this acts in. So just check the eigen. I think I solved basically that same matrix previously. But the eigenvalues, so the eigenvectors, which I was calling E's. So indeed in the R or the T direction, it's called T because 1 over, remember when you want to figure out the critical exponent nu, it's 1 over YT, but we've been calling TR. So that one keeps the same axis, so it's just like before. But this one has a transformation. I think it's the same. Is it the same? I think it's the same eigenvector. Yeah, it has to be. Because the Wilson-Fisher fixed point occurs on that axis. So. It's the first cumulant case.
What happened to epsilon?
Where's my epsilon? What do you mean? Oh, in the eigenvectors?
It's not diagonalized, but just the eigenvectors, just the diagonal component.
The eigenvalues are just the diagonal. So they have epsilons. You mean in the eigenvectors?
Oh, yeah.
Yeah, they pop. Yep. They're gone. You need them here though, or it's crazy. So they're telling you something about the distance, but okay. So, so the Gaussian fixed point. So let's draw this. So the Gaussian fixed point was unstable in both directions. Remember, we're talking d minus 4. So let's just concentrate on that. D less than 4. So really epsilon is equal to 1 or 2, say. So the Wilson-Fisher fixed point has a position. So I can use the same diagram as we used for the, look back at your Gaussian diagram. I'll use the same one. So I have a Gaussian fixed point at the origin. And now I have the Wilson-Fisher fixed point at some distance from the origin in this coordinate system, right? So Gaussian fixed point at U. So in the Wilson-Fisher at, well, at these values. Actually, does that lie on the axis of the scaling variable? Yeah, it does. It has to. Right, so. You just got to factor that out. So it's in the direction of E, U, right? But it's that distance away from the origin. So which is proportional to epsilon. So it's epsilon away from the origin. Let me see if I can draw this. Okay, so I'm going to label this R and U. And R is also what? ER or ET, right? But there's another axis that looks like this, remember? Corresponding to, I don't know, this direction. So here's the Wilson-Fisher fixed point, or so here's the Gaussian fixed point. Remember, we already analyzed all the flows for that for d less than 4. So they're all moving away, relevant. And then order epsilon along this axis from the Gaussian fixed point is the Wilson-Fisher fixed point. So the new one. And all you have to know is what's relevant and what's irrelevant. So if we take epsilon positive, well, it has to be positive for this. So then YT, or R, is what? Relevant, right? And U is irrelevant. So I should draw my axis also for. So Wilson-Fisher fixed point has the same axes. And this one's relevant. And the fact that this one's irrelevant matches the expectation that you're along this, this axis from the Gaussian fixed point. So that's important, or else you would expect some intervening other fixed point, I guess. Okay? So you have other flows in here, that generally look like that. And remember, that diagram is all the space of R and U couplings. So basically it all boils back to the Hamiltonian. Different couplings in your Hamiltonian. You land on different parts of this RG flow diagram. There's what is called a basin of attraction along this line to the Wilson-Fisher fixed point. So that's what universality is, remember. If you have some, I don't know, Ising model that boils down to this kind of phi-4 theory with some crazy R and U's, you'll just land out here somewhere. And then no matter what the underlying R's and U's, if you can tune them, if you cross this line, then the physics of that phase transition, which you'll observe, is the physics of this fixed point, because you flow to that fixed point. That's how you read these things. It's the, it tells you which, it tells you what controls the physics of whichever regime of parameters you're in. As long as your Hamiltonian is described by that field theory. Questions? Okay, so that's like the most non-trivial thing that we'll do in this class. I still want to talk about it, but we have exponents, right? Critical exponents associated with that Wilson-Fisher fixed point. And we know how to calculate them now because we know how to get the scaling dimensions and relate those critical exponents, right? So we should have epsilon corrections to the critical exponents. And when you look at the Ising model on your computational project, which I'm going to hand out now, and you look at the phase transition, you should be able to calculate a numerical approximation to those critical exponents, because the physics of the Onsager transition and the 2D Ising model, 2.269, it's controlled by the physics of that Wilson-Fisher fixed point. So what we calculate analytically now should match what you calculate numerically on your computational project. But there's two approximations going on. One, this nonsense with epsilon being an integer, and you're going to have to set it to 2, right? But on the other hand, computationally, you're on a finite size system. So there's no true thermodynamic phase transition, and you have to use this scaling theory that we developed. So let's just set up, maybe I can calculate the exponents real quick. If I do it sloppy, I can do it real fast. Okay, well, maybe it's worth writing this down. So all that stuff I said in words. So I think it's important to reiterate that if you're not on that basin of attraction, that line, then all the other points in that RG flow to either the paramagnet or the ferromagnetic phase. And again, that line, this line is called the basin of attraction. That's what gives universality. That's what we were sort of chasing. Critical exponents. Critical exponents are a feature of the fixed point. So we have Gaussian exponents, so we should have different exponents for Wilson-Fisher. And they'll just depend on epsilon. YT, we already got that one. No, minus. Jeez, man. So we're going to do lots of expansions, assuming small epsilon. So that's the correction to the mean field nu. So when you do your computational project, you just plug in 2 there. And that's what you're comparing your numerics to. How exciting. What else? We can do alpha. Because alpha only needs y. Yeah, okay. Remember, alpha was always 0, right? So, okay, let's expand that out. Yeah, that's fine. Let's write epsilon in terms of d minus 4, and then set d equals to 4. I don't know if that makes sense either. Let's try it. I know what I'm trying to get. So that's an approximation, right? So let's see, 2. I think I'm doing too much work here. Let's get rid of those 2's. All right, let's set. Man, this seems... Okay. Yeah, that's what I wanted, epsilon over 6. That seems crazy. Okay, so at least alpha is no longer 0 up the first order in epsilon. So we've always had this issue with the, the critical exponent for alpha, for the specific heat. Specific heat's important. It's one of the easiest measurements. You'll measure it numerically. And what you'll want to do is do a scaling collapse of specific heat. Numerically, what you need is an exponent for the y-axis for that. So now you have an alpha, at least up the first order in epsilon. Everything else we need a magnetic field for. But that's okay. When you need y, you have yt, you have yu, but you need a yh for many of the other exponents, right? So it means your Landau theory needs a term linear in the field, right? So we haven't done that. You got to put that back in and redo everything. But presumably it's not that hard. So okay, say minus B field linear in phi. Okay, I won't torture you with actually doing it. So what you'll get is a RG scaling equation for H. So I could ask you to add H onto that diagram if I wasn't too lazy to mark it. It's actually not hard to get that, because it's so YH, that's what I want. So it's 1 plus D over 2. Oh, this in terms of epsilon. When in doubt, add 0. So then I'll have D minus 4, right? Yeah, that works. So 3 minus 1/2 epsilon. Sure. Okay, so from that you can get all the other exponents. You just need this YH. So then gamma, you need the field, you need the scaling dimension of the field, because the susceptibility is like a response function to an applied field, right? So when you apply a field, right, it's the derivative of the magnetization with respect to that field. That's why gamma, needs YH in it. Can you get these from the hyperscaling relations if you don't have y of h? I don't know. I never thought of that till just now. That's another thing to check. So here's your correction. This was always 1. Now it's 1 plus epsilon over 6. And B, let me just write it down. Beta was always a half. Now it's a half minus epsilon over 6. Oh, I forgot about delta. Three plus epsilon.
Is it for the Gaussian and Pointro for Wilson-Fisher?
Wilson-Fisher. These are all Wilson-Fisher. Because this is the Wilson-Fisher value of y of t that we're using, right? So we're starting with this one here. But these exponents depend on the scaling dimensions t and h, not u. So so this doesn't come in necessarily. They're the thermodynamic relationships. That's why they relate to the temperature and to the magnetic field. So next time, I'm going to talk about this thing that I've been sweeping under the carpet. All the irrelevance of the phi 6 and everything like that. So it's the only piece of the calculation that we've just kind of, glossed over is the fact that the Landau-Ginzburg-Wilson action doesn't look self-similar. It seems like it's spawning higher order terms in the field. So we're just going to address that in terms of the relevance or irrelevance of those. And let's see, I'm going to talk about, let's see if we'll do that next time. I want to also look at higher order terms in the epsilon expansion. So I'm not going to calculate them, but I'm going to show you what they look like because they look crazy. So something goes crazy when you have a higher order epsilon. So we'll talk about that next time. Then I'm done with the Wilson-Fisher fixed point. What we're going to do is we're going to move to continuous symmetries. You've already done lots of work on these on your assignments. So ON models. We're going to derive the nonlinear sigma model, and we're going to also get to Koslitz-Salas equations and the Koslitz-RG equations, which were basically the subject of the Nobel Prize this year. So I think someone on campus should know what they are.